Next we have to study about control state diagram corresponding to our control logic. That is how to derive a state transition diagram from our flowchart and data processor specification. This was our data processor specification for our one flip-flop per state method, and we have B register, A register, and this corresponds to the sign bit of B register, and this is the magnitude corresponding to B register, and this is the sign bit for A register, and this is the magnitude for A register. This is used for storing the carry out during the operations performed by ALU, and these are the select lines, and this is the load input. Okay, and this is the this was our control logic block diagram, and we have a number of 5 inputs, and that is 2 from external environment, 3 from the data processor, and these are the outputs, control outputs. So we can consider our state transition diagram corresponding to control logic. So design of a hardwired control is sequential logic problem. As such, it may be convenient to formulate the state diagram of the sequential control. The function boxes in a flowchart may be considered as states of the sequential circuit. So we can easily derive the state transition diagram from our flowchart. The decision box may be considered as next state conditions. The micro operations that must be executed at a given state are available from the function box of our flowchart. So this is our flowchart. This represents the initial state. Then if QS is equal to 1, that means if the QS 1 means there is a subtract operation that indicates we need to perform a subtract. In that case, simply complement the sign bit of the second operand, then reach into this state, this block, and if QA is equal to 1, that means addition, then bypass this step. This step is to reduce the operation into addition only. If you have to perform subtract operation, we will simply reduce that operation into an addition operation by changing the sign of the sign bit of the second operand. Okay, then if AS is equal to BS, if the sign bit of the both operands are same, then simply perform the addition of the magnitudes A and B with the help of our ALU. So the corresponding control signals will be given, and addition operation will be performed. The C out will be stored into E register, okay, by enabling the load input, activating load. Then goes to the initial state, and X will become 1. That will inform the external circuits that operation is completed. And if the sign bits are not equal, then perform a subtract operation on magnitudes. That is, we will perform A minus B, magnitudes A and B, subtract operation with the help of our ALU. That will be done by using our control signals, giving particular control signal. Then E will be stored accordingly. E is equal to C out. Then if the value of the E is equal to 0, that indicates A is less than B. That is, the magnitude of the magnitude A is less than magnitude B. In that case, the result is not in correct form in A register. So this will be in negative form. But in sign, we are using a sign magnitude for the entire representation. So we have to make this one a positive one. For that purpose, what we will do, we will find the 2's complement of this result and then complement the sign bit. Okay, that is here, that is we are doing here, that is A is equal to A complement. and a is equal to a plus 1, because there is no separate separate operation of 2's complement in ALU, no operation. So what we will perform a 1's complement and increment operation, that is equivalent to 2's complement, that is a is equal to a complement, then a is equal to a plus 1. Then invert the sign bit of this result. Okay, then goes to the initial stage. That was our flow chart. This is our control circuit or control logic. Then we can simply consider the subtract operation of plus 2 and plus 5. Okay, what will be the how the flow chart will work? So this is the binary equivalent corresponding to, in sign magnitude form, plus 2 will be represented like this, that is stored in A register, and plus 5 is this one, that is stored in B register. So sign bit is 0, here also 0. This is simply the representation corresponding to 2 and 5. So this system will be first in initial state, and then it check for the operation to be performed. We have to perform a subtract operation, that is QS is equal to 1. Then we want to, or we have to reduce this subtract operation into an addition operation, or convert that into an addition operation. That we will do by simply changing the sign of the second operand, that is BS is equal to BS complement. This is our B register, this is the BS. So simply complement that one by giving Y a 1, Y control signal as a 1. So this will become complemented. Now this will become minus 5 in sign magnitude form. So, and the operation can be reduced into plus 2 plus minus 5, that is just like an addition operation, but the operands have different sign. Okay, so we will reach here. Now this algorithm or this part is common. This is for addition operation only, but the operands may have different sign. So we can use the same part for both subtraction and addition. That is the significance of this reduction. Okay, so now we have to perform plus 2 and minus 5 operation. So we have reached here AS, BS. If they are, we will check for the sign bit, they are equal, but they are not equal. So we'll reach into this block. We need to find the we have to subtract the magnitude parts A and B. Subtract B from A. Okay, for that purpose we can use our ALU. In the case of ALU, inside this ALU will use the 2's complement arithmetic. Okay, so for that subtract operation we have to give a 0101 code. Then ALU will take the 2's complement of this one, this magnitude part, and this will be symbol like that, because we have to perform, we have to take in this 5 minus 5 in 2's complement, that will be like this, because ALU will perform only in using 2's complement arithmetic. That is why ALU will take the 2's complement of this 5 to make that as a minus 5 inside the ALU, then perform the operation. So 0 plus 1 1, 1 plus 1 0, 0 plus 0, sorry, this carry plus 0 plus 0 1, and the carry out will be 0. Okay, this will be the result. So now we got a result like this. A register has 101 and carry out is equal to 0. Okay, but the result is not in a correct form, because in our case we need a sign magnitude arithmetic. We have to perform the final result must be in sign magnitude form, but the result in A is not in correct form. because here it is in 2's complement form. So we need to convert back it into the sign magnitude form. What we have to do, just find the 2's complement of this again and invert the sign bit. Okay, we reached here. Actually we reached here. E is equal to 0, that is the case, and a is equal to 0 means a is less than b. A is less than b, and the result will be in a, so the result will be in negative form. A is less than b. If you are performing a minus b, the result will be in negative form, just like this. So to convert into sign magnitude form, we have to make the 2's complement of this again and invert the sign bit. That is the case. Okay, so but 2's complement can be performed by using 1's complement plus 1. Okay, so first we will find the 1's complement. The corresponding code will be 0 1 1 1 0, 1's complement. Then increment the content of a. For that we have to give another code to ALU. So we are giving 0 0 1 is the code for increment operation. Then the A register will become 0 1 1. Now next step is we have to complement this. AS is equal to AS complement, this part. So give a 1 at the Z, then that will be complemented. Okay, now the result is correct. This is in sign magnitude form. 1 indicates minus, this equivalent to 3, so minus 3. That is how the how addition and subtraction can be performed in the case of in our hardware, by using our hardware. We have designed a special, this is only for study purpose, not an actual case, to understand how to design control logic. Okay, so this is working of our flowchart. Next is we have to derive state transition diagram from our flowchart. So initially we will be in state T0. Okay, T0. So in that initial state x is equal to 1. X, the control variable, control output, x will become 1. That is the operation to be performed there. Then if QA is equal to 0, QA is some input for starting addition, and QS is the external input for starting subtraction. Okay, then if QA is equal to 0 or QS is equal to 0, that is no control inputs from external circuits, then our system will reside in the state T0 itself. There is no state change. These are the QA and QS are external inputs. Okay, this is actually A register. By mistake it is written as B register. Okay, so okay, then if QS is equal to 1, then wheel goes into, okay, now we are in this state, and if QS is equal to 1, then wheel goes into this state, this block. So corresponding to this block we need another state, that is our T1 state. So if QS is equal to 1, a subtract operation, then wheel goes into T1 state. In T1 state we have to do BS is equal to BS complement. That is the operation to be performed in T1 state. We reached here, and during the next clock pulse that will goes to this state. Okay, so during the next clock pulse or next clock cycle, this will goes into T2 state. Just in T2 state do nothing. Okay, and if the operation is a add operation, then there is no need to execute this one, just goes to this one, this state. So if QA is equal to 1, simply change the state into T2. There is no need to go to T1, just go to T2. Okay, now we are here. If the AS and BS are equal, what you have to do? We have to perform A is equal to A plus B and E is equal to C out. So we need another state corresponding to this one. And one more thing is, in our control logic, this AS and BS are XORed to form a new signal called S. Okay, so when both the signs are equal, the S output will be 0, because AS XOR BS will be 0 in that case. And if both signs are different, if these signs are different, then the S value will be a 1. That will be used in our state transition diagram. Okay, if S is equal to 0, we have to go into T3 state. T3 was our A is equal to A plus B and E is equal to C out. And both have the same sign. And if they have and then the next state is T0 itself. Okay, after that will goes into initial state. This is the from T3 to T0. Okay, and these are in T3, these are the operations to be performed. Then if they are not equal, the sign bits are different, we have to go to this state corresponding to this box, function box. Okay, so we can make another state for this function box. The operations are A is equal to A plus B complement plus 1 and E is equal to C out. So if S is equal to 1, that is the signs are different, then go to another state T4. In T4, the operations to be performed are A is equal to A plus B bar plus 1 comma E is equal to C out. This is actually A minus B operation. Okay, now we reached here. Then next state is T5 state. In T5, do nothing. It is actually here, we reached here. Then if E is equal to 0, is equal to 0 means A is less than B. In that case, we will reach into, we have to create another state corresponding to this block. A is equal to A complement. That we are doing here. If E is equal to 0, T6. In T6, we have to perform A is equal to A complement. We can go to the next block, or we have to create another state corresponding to this block, function block. There is no condition, so during the next clock, unconditionally that will goes into this state. A is equal to A plus 1 and AS is equal to AS complement. So from T6, during the next clock pulse, that will goes into T7. There is no condition, just for the next clock pulse, that will goes into the on the next clock pulse, that will goes into the T7 state. And the operations are A is equal to, the operations to be performed in T7 are A is equal to A plus 1 and AS is equal to AS complement. And that will goes into the initial state during the next clock pulse. So on the next clock pulse, that will goes into initial state or T0. Then if E is equal to 1, that is A is greater than or equal to B, in that case the result will be in correct form. After performing the subtract of A and B, the result will be in correct form, because the result will be positive value. The magnitude, if you are considering the magnitude only, A is greater than B, then in that case we have to simply make the E is equal to 0 and go to initial state. So we make another state corresponding to this block. E is equal to 1 T8, and during the next clock pulse that will goes into T0. Okay. If you are looking to this T8, actually we can remove this T8 from our state transition diagram by performing the operation E is equal to 0 in T5 itself. Okay, then we can remove the state T8 from our diagram like this. We have just we have just moved that operation into T5, because previously in T5 we are performing nothing. That is used only for some decision making, that is E is equal to 0 or E is equal to 1, but we are just moving this E is equal to 0 into here, and we can remove the T8 from our state transition diagram like this. How this will be possible? Because in all these states we can consider this first. From T4, what is the operations performed on T4? A is equal to A plus B bar plus 1 and E is equal to C out. So these operations will be performed only during the next clock cycle. Okay, so during the next clock cycle these operations will be performed, and the state will be now in T5. Okay, similarly in T5 the operation is E is equal to 0, but this operation will be performed only during the next clock pulse. So currently the value will be the previous value or the original value. So we can make the checking here, E is equal to 1 or E is equal to 0. E is cleared with the clock pulse that causes control to go out of state 5. The original value of E determines the next state. So here we will perform the checking, and after that during the next clock pulse only E is equal to 0 will be updated. That is why we have reduced like this. Okay, so this both are equivalent. The previous diagram and this diagram are equivalent. Okay, but in this case we have reduced one state. In all the states the operation is similar, because the operations will be performed during the next clock cycle. Okay, so this is the state transition diagram corresponding to our control logic. We have to derive expressions corresponding to each of the control outputs, and also inputs corresponding to the flip-flop for our control logic.